Good morning and good afternoon. So this is the FRQ number 3 for the 2026 that we are going to be making. So in this FRQ that we are going to be use the concept of the basically the torque that is related to that one, and the one part of the question is related to the buoyant force also, that also we are going to be studying that one. So let's come to the screen, please. So let's start that. So this is the FRQ number 3. So let me quickly, I request to you, please go through that FRQ. So this is the, then look into the video. The question is, a student has investigating the balancing of the system. That is the setup that you can see it here. So we have the scale, meter stick. On that way, on the one of the side, we have the spring scale, and the other side you can see these holes. So these are the holes that they have marked it, small holes that they have marked it. And you have the block of M naught unknown mass. And you had to be put it here at the different positions. And you can mark the spring scale, how much the spring scale is measuring the. This is unknown. In the question, we find out this unknown mass only. You can't measure from the spring scale is. You had to be make the graph for that. So the first one is the first question is that we had determined the experimental measure of the collected data, that could the student determine the M node and indicate the step and the necessary experimental uncertainty that you can cause. So experimental procedure to collect the data. So here the thing is that we have the spring scale on the one of the side and the block. I had to be make the experimental procedure to collect the data. So let me quickly do that one. So this is a meter stick that is have the center of the mass of the meter stick at this point only. So it will not provide any kind of the torque about this point. So you are going to be hang the mass here, and you are going to be measure the how much the force that is in the spring scale is. So and this distance is, so this distance is fixed only, you are not changing this distance. So I'm going to call it this distance is RS, and this is the, so let me call it this is R something, R for the block I'm writing, let's suppose B. So this is RB, and that RB is, I'm going to keep on changing that one. So if you place it at the different position, it will provide the different torque. So accordingly, the spring scale is going to be measure the different values of that. So in the first case, what you had to be, you had to make a table. So I'm giving the rough idea first. So you had to be quickly make a table. In that table, you are going to be measure the at the different positions, what the positions are, and the force of the spring, how much it is, and this distance is the fixed only. So RS, I had to be measured. This is 50 centimeter only. 50 centimeter. Remember it, you have to convert to the meter, and then we have the every time we are going to be put the m naught mass at the different positions. So this is the length, so the RB value that I'm going to measure that. So this is the table that I had to make it. So let me upload it. So the first part of the question, you had to be set up a meter stick. It is pivoted to a stand, and the center of the mass is 50. So it is a balanced one. So that is the meter stick. So that had to be balanced. So there is no net torque due to the meter stick. That is very important in this. Then we have the attached scales. The hook, the spring that is fixed to the left of that one, the meter stick. You can hook that anywhere. So this is hooked at the 50 centimeter from that one is, and the distance that is from the spring balance, that we call it the RS. Hang, we had to fix that one. The spring the scale that we had to fix that one. Third one is hang the block of the unknown mass m0 to the specific hole in the right side of the meter stick. Let the distance from the pivot point of the block is the RP. So this is the RB where you put the m0 mass will be. This is the m0 mass where I'm hooking that. So everywhere I have to keep on changing the position of the m0. Take a measurement and pull down the spring until the meter stick is perfectly horizontal, and determine the force of the reading of the RS from the spring scale and the distance RP. So every time you had to be uh, put the masses at the different position until unless it will not balance it out properly. So you have to keep on doing that one. So, and this experiment, take a measurement, then repeat, move the block at least the fourth position of the hole that is mentioned over there, and accordingly you had to be keep on measuring the required the spring um, scale force, that how much you require that one, and what the RB, the distance where you are putting that. You have to keep on changing that one and you will get that. Reduce the uncertainty. At each of the position, take at least the three separate force reading and average them, and ensure that the spring scale is pulled exactly the straight line and something 90 degree, and the meter stick is avoid the error in the torque. So we are going to be calculate the torque for that. So you have to keep on repeating that again and again so that you can decrease the uncertainty over there. Now, the next one is describe how the data collected in the A part could be the graph and how the graph could be analyzed to determine the M naught value. So let's do the thing as we discussed that one. So let's do the further bunch of the calculations. This one I hooked that one, the spring scale at the 50 centimeter from this point is from this end. And from the other end, let's suppose this is the RB, this is the distance that is, I'm going to keep on varying that one. So this is the M naught mass that I hooked that one. At this position, M naught mass that I hooked that. So it is going to be provide the some kind of the clockwise torque, and this is going to be provide this force, the spring force is going to be provide the anti-clockwise. So this is the clockwise torque. It is going to be provide. This is anti-clockwise torque. How much the clockwise torque is? Clockwise torque is, to find out the torque formula is this perpendicular distance into how much the force that is acting. Due to the mass, the force will be mg force where you hang that one. So m naught g. So this is the force into perpendicular distance. This is the 90 degree the distance is. Otherwise, the torque is, remember it, the torque formula is torque is equal to force into R perpendicular, you can write it to find out the R perpendicular. So I have made the separate lecture for that one, the torque one. You can get that one on the channel only. You can check it out that one. Those the torque into perpendicular distance. For the perpendicular distance only, we write it R sine theta. Actually, the formula is FR sine theta. So the theta is 90 degree here. The force, the angle between the force and the R value, the resistance value that we have it. So this is a torque. So right now it is 90 degrees. So the force is right now MOG that is acting on the one of the side. That is a RB, the distance that I'm taking it. And this is clockwise. In the same way, anti-clockwise, that is the spring force, and the RS, the distance that I'm taking. So the spring force and the RS, where you hang that one. So it depend upon the where you fix it that one. So it depend upon that one, the spring force. So let's equate both of them. So the clockwise is MOGRB, and because it can balance it out, so the torque have to be equal on the both the side. So this value You already know that spring force, you can already know that on the scale. So the M naught value is come out to be, so they are collect the data from the M naught and something from the graph and could be determined this one. So let me do that calculation. So the torque value, M naught value will be come out to be FSRS divided by GRB. Correct. So this is the M naught value will be. So, but we had to make the graph for that one. To make the graph, I have to be take any kind of the x-axis and the y-axis, the parameters that I needed. So I'm just changing the, so M naught I had to be make as a slope or something, the constant parameters, and the two parameters that are changing here, this value and this value. So I will not advise you to rearrange like that. So what we can do is we can take it. So what I advise to you, so do not write like that. Keep this thing. So the keep this thing only. So M node G RB divided by RS. RS is the fixed parameter. RB is a changing parameter. So the FS. So let me rearrange one more time. So I'm just writing the RB that is changing. This is on the y-axis, this is on the x-axis, and this parameter that I'm writing as a slope on that. So I can write like this. So on the y-axis, this is capital Y, this is mx plus c. So there is no y-intercept right now. So this is c. So this is the x-axis, this is the y-axis, and this is the slope. So you can literally find out the slope for that one by taking this is the parameter that we have it. So if you want to study that one, this is the one of the solution that you can look into that. So if you want to go through that one, thank you. Now let's move further then. Now we have the next part of the question is, so now we have the wall. On the wall we have the string, that in the string we have the spring scale, and we have the meter stick. Now that meter stick is have the axis here, that is frictionless axis. So there is no loss of the any kind of the energy over there. And so this is 60 centimeter, total is 100 centimeter. This is a meter stick. So you can, again, they have put the hole. So accordingly, when you join these two and the meter stick, so it will show the different tension forces in the string. So there is a tension force in the string. So they already given the table here at the different angles what the tension force value will be. So you can see that when the angle is smaller, the tension is the more over there. So it means that if you hang it here like this at this angle, I think. So this is, if you hang it here, so the angle is 22 degree and the 22 degree. So tension force in the string will be 21 Newton. So the point here is they already given that one. So you do not have to be worried. And as you have the bigger angle, so you require a tension force component is lesser over there. Now the question is, even you can analyze that one. So this tension force is balancing by the way every time the mg force or mg force of the meter stick, that is balancing out by the one of the tension component. So if I had to take the tension component here, so let me write that one so that you can analyze that one. But in this question, we do not require it, especially. So to analyze that why it is happening. So this is a tension force. This is Ft tension. And this is the, if this is the theta, this is Ft cos theta component. And this is Ft sine theta component. That Fc sine theta component is balancing out the mg component every time. So as you increase the theta, the sine theta value will also increase. So you required a less uh, tension force to balance it out the mg, because mg is not changing, correct? That is constant. So if it is, this value will increase. So the another, this side is constant only, that is not changing. So the F tension force have to be go down basically. And this is the thing. So, and they already given that one, so you do not have to worry about that much. The correct to determine the ft and this one, this is the tension value, whatever the way that they have calculated, but this is the ft value that they have get it here. So 1 by sine theta plotted on this one. So this is the first of the question is vertical axis you have to determine. Horizontal axis is already given. So the horizontal axis is already given. The vertical axis is. So you have to just rearrange that. Just let's do the rearrangement. So let's do the calculation. So this is ft. So I can write it ft on the y-axis. And this is mg and 6. And this is 1 by sine theta. And this is already they have given it on the x-axis, so you can again compare it by the y is equal to mx plus c. So there is no y-intercept that we have it. So this is the slope basically, and the slope is this much, and that slope you draw the graph, and that slope will give you this parameter, so you can calculate the m value from that parameter. Let me give the graph also with. First, you have to complete the table, that is sine theta, 1 by sine theta, and the ft. So these two, they have already given the theta and the tension force. You required sine theta and the 1 by sine theta, and you will get the graph like that. You can line of best fit. You can curve that one accordingly. You can find it out. The slope, from the slope, you will get this parameter. So basically, the slope is this. From that, you can calculate the m naught from the slope equating that one. I hope so you get that one. So let me, the slope, whatever the slope that you get it, just equate to this value. This is the thing that we have it. Thank you. So now let's move to the experimental. You can calculate that one, but in this case, let me give that value also to you. So this is the value that you will get that one. So calculate the slope from the graph and just equate to the this value, and from there you will get the capital M value that they are asking to calculate that one. Mass of the meter stick basically. Next part of the question is regarding the buoyant force. So we have the swimmer mass M, the block had the mass M, rest on the tanker. So this is the density is rho1 as shown in the figure. The block is released from the rest and accelerate upward, and the acceleration of the initial acceleration is a1. All the friction forces are neglected. Case 2, the swimmer hold the same block of the tanker. So basically it have the same volume basically, and but it is now it is a salt water. Salt water have the more density. The swimmer again release it out the block from the rest and accelerate that one. So we had a two acceleration. In the first case, the acceleration in the fresh water, the acceleration of the block upward in the second case. So now the question is determine, indicate whether the A naught is the greater than that, less than that. So which condition it is going to be satisfied. So let's learn about some kind of buoyant force also. So what is a buoyant force? It is a upthrust force that the fluid, any kind of the fluid will apply upward. As it is, any block is submerged into the water, there is a upward force that the force act against the gravity force. So if you uh, drop any other thing, the object into the water, so it come down, correct? Because so as this pan, I leave it in the water, so that due to the mg force, it drag it downward. So there is a upward force, that is the buoyant force, that is going to be acted upward to float that. Think logically, if the mg force is down more, so this pan is going to be sink than the upward force that is acting. If bind force is upward is more, so it is going to be go up rather than the mg force. So if the bind force is more than the mg force, it is going to be accelerate up. So they already given in the question, so it is going up, it means the bind force is up, more than the mg force, so it is going to be accelerate up. So on this block, if I had to make the free body diagram, so there is a upward force FB I'm writing, that is a bind force. The below one, that is the mg force that is acting. In the both the cases, it is accelerating upward. So there is a net force. Net force is acting it upward. So this is the net acceleration that we have it upward. So as we know that one, net force is equal to mass time acceleration, correct? Newton's second law. So the bind force that is acting minus mg force that is acting it downward. So this is the net force. Net force is equal to mass time acceleration of the object. So this is the net force I calculated. Bind force minus mg force is equal to ma, mass time acceleration. And then I had to will calculate the acceleration of that, and this is the net. But right now in the first part of the question, they are just asking what the acceleration, in which case it is will be more. Think it logically, because the buoyant force value of that one. So let me write it here only. So the buoyant force FB, buoyant force formula is rho. Let me write here. I have to write it few other things. The buoyant force, it depends upon the density of the fluid. That's very important. This is the density of the fluid. The most of the time the student just get confused. It is the density of the water or a block. So this is the buoyant force that is acting it upward. That is the we had to take the density of the fluid, because fluid is applying the buoyant force on that. Remember it. So this is the density of the fluid into the g value, acceleration due to gravity, into the volume, how much the volume the block has submerged. Most of the time, 95% of that, the block is going to be, they are going to give fully submerged into that. So whatever the volume of the object, it has the same volume as submerged object, correct? But remember it is the submerged volume. So it is how much the portion is submerged. This is a submerged volume. So how much the portion it is that is submerged, that's important. So most of the time it is, they are going to be submerged fully object only. So this is the FB. So if the density of the salt of the water that is more, so it is going to be the buoyant force will be more, correct? So if the buoyant force will be more, so the acceleration will be more, because there is a net acceleration is due to the buoyant force minus mg. If the buoyant force will increase, obviously the net acceleration upward have to be increased. So in the second case, it is going to be greater. So in this second case, it will be greater. So you have to be say this part. So that is bigger than that. Now, in the next case, they are saying that apply the Newton's second law and derive the acceleration for the basically the acceleration. Derive the relation of the acceleration. So let's complete that one. So FB, let me plug in the values. So the density of the fluid into G value into V of the object, because it is fully submerged right now, minus mg. Even we had to calculate the acceleration initially only when it is released it out, into ma of the object, the mass of that one. So this is the acceleration that is going to be come out to be, and even we can cancel out the things. So I can put it the mass here. I can put the g. So this is the net acceleration that is going to become upward. This matches acceleration of that one. So the density is whatever the density for the air, for the water, fresh water, or we are taking for the salt one. So you had to be look into that. Now, in the third case, see whether the you calculated the acceleration in the you derived in the B part just right now is not consistent to the claim of this one. It is consistent or not consistent, that is they are asking that one. We predicted in the first part of the question that if you have in the salt the density is more, so the density is more, that result in the more acceleration upward, so the block is going to be accelerate with the more acceleration. So the point is right now the density of the salt one is the more. So if this parameter will increase, so overall these all are positive quantities only. So this overall is going to be increased. The whole parameter is going to be, because the numerator is increasing, that mass is not changing. So overall, yes, that is also the net acceleration is the increasing that one. So this is the whole question is. So I will try to make the more FRQ questions also. So thank you. Keep on watching that one. Subscribe the channel. Thank you.